All right. Welcome, everyone. It's my pleasure to introduce Chris Lutsko that will tell us about the spectral theory of automorphic forms.
All right. So thank you, Claire, for the invitation, and thank you everyone for coming. So I'll be talking about spectral theory of automorphic forms and specifically thinking about the infinite co-volume case. And then in the second half of the talk, I'll think about a bit more about higher rank infinite co-volume subgroups. Um, so I will start with. Okay. I'll start with some more classical stuff, talking about spectral theory of L2 of H mod gamma. Then I will think about one specific example of one of these subgroups and some connections to some geometric and number theory objects that people have been studying. So how do we use the spectral information to come up with theorems? And then I'll explain a little bit about the higher rank spectral theory. So I intend for this to be a bit of a survey talk. Maybe now that I have lots of gray hair, I can give a survey talk. But please interrupt if you have any questions. I know this isn't everyone's wheelhouse. Okay, but starting with the basics. So we're going to start with the upper half plane, and G will be the group of isometries on the upper half plane, SL2R, acting via Mobius transformations. K will always be the maximal compact subgroup of G, and then we think of H as just G mod K. Let's fix a discrete subgroup, gamma, living in G. And we say gamma is a lattice if the hyperbolic volume of the quotient is bounded. And it's a non-lattice if that's not the case. So here's an example of a non-lattice. This is a Hecke triangle group. I think you want mu bigger than square root 2. Or is it just 2? Just 2. Yeah, just 2. Um, Mu bigger than 2. And then this first matrix reflects through the unit circle. So you can see this point Z here has been reflected through the unit circle there. And then this 1 mu 0 1 translates by mu to the right. So that translates us to the right. And then you can keep uh, translating and reflecting through the circle, and you'll get this sort of infinite fractal-like object. Okay. A couple definitions that we're going to need as we proceed. The first is what's called the limit set. So the limit set is the set of accumulation points, or really it's the closure of the set of accumulation points, I should have said, of any orbit. So if we take an orbit of Z by gamma, then it'll start to accumulate on the boundary. And in particular, for a non-lattice, we'll end up with a sort of Cantor set. It's not a Cantor set because the maps aren't linear, but it's like a Cantor set, right? None of these points can ever be absorbed into this funnel here, and so you can just cut it out, and what remains will be the limit set at the end. And if I have a lattice, then the limit set will just be all of R, right? The lattice accesses all of these points on R. You can approximate any point down here infinitely well by these lattice points. These are the Faraday fractions. Um, so the limit set is just the all of R. And then the second quantity that we need is what's called the critical exponent. And this is the exponential growth rate of points, right? So we take any point, we look at its orbit, so we apply gamma to that point, and then we take the distance from Z to gamma Z. So you're looking at this increasing ball, and you're adding up all these points with this exponential weight. And the first time this converges, that gives you your delta. If you have a lattice, then delta gamma will be 1. And if you have a non-lattice, then delta gamma is less than 1. This just comes from a sort of volume calculation. Okay, so now we can talk a little bit about spectral theory of L2 H mod gamma. So this is the hyperbolic Laplacian. It is the only invariant differential operator for this group. And we'll define the spectrum with this sigma of Laplace. So the spectrum, this is the collection of eigenvalues, but it's also more than the collection of eigenvalues. It's anywhere where delta minus lambda inverse is not defined. But if you're not familiar with this, just think of it as the eigenvalues of the spectrum. So what do we know about the spectrum of automorphic forms? Well, to start with, let's think about lattices. All lattices will have the base eigenvalue at 0. The eigenfunction is just the constant function. So we know that the base eigenvalue is at 0. We know that the spectrum has to be positive. And then there are finitely many eigenvalues below 1/4, possibly. These are the exceptional spectrum. Then you get the continuous spectrum above 1/4 coming from the Eisenstein series. And you could have some embedded eigenvalues. In fact, you probably do, uh, which correspond again to cusp forms. Okay. Now, just a bit of notation. Given a point in the spectrum, it's more natural if you want to construct like an L function or something to consider the spectral parameter, which is this S value, and we write lambda as S1 minus S. Or you might see people write it as 1/2 minus S squared. Um, yeah. Okay. So what do we know about the spectrum of non-lattice subgroups? Well, the first thing is we know that there's no base eigenvalue at 0 because that comes from the constant function, which is no longer an L2 function. Instead, we have this kind of remarkable theorem by Elstrad and Patterson, which tells you that the infimum of the Laplace spectrum is either going to be the continuous spectrum, so you just get continuous spectrum. Sorry, I'm always assuming there's a cusp at infinity. Um, that's not necessary, it just simplifies notation. Um, so apologies for that. Um, so assuming there's a cusp at infinity, then we get the Eisenstein series, which give us the 1/4. And unless delta is larger than that, in which case we get this explicit formula for the base eigenvalue in terms of this critical exponent, which I defined here, this exponential growth rate. This was extended to higher dimensions by Sullivan, extended to more general symmetric local spaces, locally symmetric spaces by Corlett. And another fact due to Lax-Phillips is that for infinite co-volume subgroups, we get no embedded eigenvalues. So we could have exceptional spectrum, and we have continuous spectrum, but we have no embedded eigenvalues. Yeah, that's a theorem. Uh, moving on, I'm going to let delta H denote the Hausdorff dimension of the limit set. Then another theorem, due to Patterson, Sullivan, and Corlett, at least for orthogonal groups. This O just means you take the connected component. Then the Hausdorff dimension of the limit set is equal to the critical exponent. So this all of a sudden gives you a framework which you can use to start analyzing these groups because the limit set is usually just some fractal, and you understand the rules for making that fractal, so you can work out the Hausdorff dimension. This gives you the critical exponent, which tells you some geometric information, but it also gives you the infimum of the Laplace spectrum. Warning that this theorem is not in general true. Uh, that there's an example by Duflo in rank 1 where this theorem is only true if you change what Hausdorff measure you're using here. Um, yeah. Okay. And the last thing that I want to talk about before talking about new things is matrix coefficients. So if I'm given a unitary representation, some Hilbert space, I can define the matrix coefficient to be the function that takes G to V inner product W, and then I've acted on V by G. And we say that a representation is strongly LP plus epsilon if, uh, as a function of G, for fixed V and W, these matrix coefficients are in LQ for Q bigger than P. And we say a representation is tempered if it is almost L2. So what's the point of these representations? Well, the first is that by studying the L2 space, we really are studying these representations, and that it's enough to study L2 of G to understand these representations for this Lie group. And the other thing is, if you stare at this long enough, you start to realize that it's a form of mixing. So what we're talking about is controlling the decay of this function. And if I stick, instead of a G, I stick like a geodesic flow here, then this really does look like mixing. So it's kind of quantifying mixing uh, for the group. Okay, and then we have a generalization of some work of Elstrad and Patterson shows that this L2 space on G mod gamma is tempered if and only if delta gamma is less than 1/2. So you yeah, and then you can actually quantify the decay of matrix coefficients when delta is larger than 1/2. So the point is that either your spectrum is just the imaginary axis, in which case the L2 space is tempered, and we can't say anything about base eigenvalues because there isn't one. Or we know what the base eigenvalue is. We don't have temperedness, but we have control over the decay of matrix coefficients. Um, and we know what the base eigenvalue is. Okay, so here's the picture, right? We have exponential growth rates of elements are related to bounds on the bottom of the spectrum, which is related to the decay of matrix coefficients, and then these are all if and only if statements. And then we have this Hausdorff dimension, oops. We have this Hausdorff dimension thing in some cases. So in the second half of the talk, I'm going to explain what we know about this trichotomy in higher rank. But for now, I thought I would start with an example of how we use these spectral and geometric information to study more classical problems in number theory and other things. And the example I want to use is the Apollonian counting or the Apollonian circle packing. So to get the image on the right, you start with the image on the left, and wherever you see a gap, you fill it in with a circle which is tangent to all of the circles that form the boundary there. So I fill in these two dotted circles, and then I can fill in 1, 2, 3, 4, 5, 6, and then I can fill in the next, whatever, 12 or something, and keep going, keep going, keep going ad infinitum, and you end up with this packing. Um, I find these really interesting structures. They actually show up in nature if you take a bubble bath and you look at the bubbles, they will be tangent, but they won't overlap, of course. Um, and so you get these kinds of packings. They show up in number theory because the relation between the radii of these circles is given by some quadratic form. So you're really, if you're looking at the radii of these circles, you're really looking at integer values of some quadratic form living on a group orbit. Um, so hopefully you think it's interesting. Um, well, I guess it doesn't really matter if you think it's interesting. It's what we're talking about. So the question I want to ask is, how many circles are in this packing of radius larger than 1 over t? This is it's a reasonably classical question. So what does this have to do with what I was talking about? Well, if we place the packing as the boundary of H3, so that's R2, then it turns out you can write a generating group in SL2C, which generates the packing. And the generating group, the generators of this group, are given here as hemispheres perpendicular to the um, to the boundary. And I would say what I've done, no, what Alex Kontorovich has done is take a point and then take its orbit, or I think he's taken 4 points here and taken their orbit. And what you can see, maybe I can shoot. What you can see is that the packing is showing up as the limit set of this orbit. So this isn't the packing isn't drawn there. This is the effect of these points accumulating on the boundary. Um, yeah. So we can realize the Apollonian circle packing as the limit set of a infinite volume, infinite covolume subgroup. So what's nice about this? Well, the packing is generated using some pretty classical maneuvers, and you can work out the Hausdorff dimension of that. Not precisely, but you can get estimates, and that's Boyd got some inequalities. McMullen was the first person to get uh, a sort of real estimate. Um, and then Karlovitz, I think, improved it, and I don't know. They have several hundred decimal points now, and I don't. I've lost track of who has the record, but we can use that theorem of Elstad and Patterson to say that now we know what the infimum of the Laplace spectrum is. You might be concerned that this is bigger than a quarter, but since we're working in SL2C, that 1/4 gets shifted to 1. So your exceptional spectrum happens between 0 and 1, and then you have continuous spectrum from 1 forwards. Otherwise, it's the same. So now we know exactly where the bottom of the spectrum of this uh, of the Laplacian for this L2 space. Not only can we quantify the decay of matrix coefficients, we can actually make that effective. So where the rate of decay depends on the spectral gap, so the distance between 0.907 and whatever comes next. And then with Duby-Kellner and Alek Kontorovich, we answered a question that Sarnak had written in a letter to Ligarius, and we showed that the Apollonian packing has maximal spectral gaps. So there's no spectral information from this eigenvalue all the way up to 1. And so putting together all of this information, we actually know everything there is to know about the spectrum of the Laplacian on the Apollonian group. We know where the base eigenvalue is. We know that there is no exceptional spectrum. We know that there are no embedded eigenvalues, and we know that the continuous spectrum starts from 1. So really, we have all of the spectral information for this group. And what can you do with it? Well, using that spectral gap and using some of these methods, you can get a very nice approximation for this count. Yeah. And you can get all sorts of other things like statistics between the points, the centers of these points. Yeah, and then some number theory implications. You can sieve if you want to sieve. Yeah. And this was building on work of Boyd, who got the first asymptotic, but he didn't get the constant. Kontorovich O, they got the constant. Lee O and Vinogradov got effective results, but not as strong. Okay, so that's what we can do with the spectrum when we know something about the spectrum. We can get very good asymptotic formulas um, with effective decay rates. So now let's move on to higher rank. And again, my goal will be to recreate that trichotomy that we saw earlier, but now in higher rank. So G will just be a general, real, connected, semisimple Lie group with finite center and rank R. We define the maximal compact as K, in which case G admits a Cartan decomposition. So you should think of this as, okay, the example you should think of for G is SLNR, or 2 copies of SL2R, if you want to be even more simple. Um, then this is just a standard decomposition. You have, if you start with a vector in H, you change its direction so that it's pointing at a different vector. Then you apply the geodesic flow, and you travel there, and then you apply K to change your velocity vector back to what it should be. So this works out the same, except that now, rather than having a 1-parameter geodesic flow, we have a 2-parameter or an R-parameter geodesic flow. So the distances are now measured in vectors in a way. Given a G, if we write it in its Cartan decomposition, then the A component is like the distance. That's like the geodesic distance between 2 points. And so using this, Qua was able to introduce a definition which takes the place of the critical exponent. So remember, the critical exponent was the exponential rate of growth of an orbit. However, now that we're in higher rank, orbits can grow in different directions. And so our exponential rate of growth is going to depend on the direction that we choose. And so we have to choose, well, we do choose an open cone around our chosen direction, and then just take the infimum of that open cone. So we're really just trying to get the contribution from the points growing in one single direction. Okay. And it turns out that this is a good replacement for the critical exponent. Okay. Now, before, when we were talking about spectral theory, we were talking about the spectral theory of the automorphic Laplacian. In higher rank, there are more invariant differential operators, and so they form a full algebra of invariant differential operators. And so the spectrum, so if I want, let's suppose I have an eigenvalue, it will have to be an eigenvalue of the generators of this ring, and it can be a different eigenvalue for each of the generators. But then you can construct new differential operators by taking linear combinations of the old differential operators, and you should still get an eigenfunction. And so our spectrum is now given by characters, right? Or another way to think about that is you can parameterize it by c to the rank of g mod k. So before we were looking at spectral parameters living in C. Now we look at spectral parameters living in R copies of C. So here's a picture. Um, so the real plane is given by two dimensions. The imaginary axis we've collapsed into one dimension. It really should be two dimensions, but I'm bad at drawing in four dimensions. Um, You have the half sum of restricted roots. So this just measures how quickly volume is changing in different directions. So it's a functional on A, on on the diagonal flow. And it measures how fast volume is changing. And so if you had a lattice, then you would know that your spectrum would have to live inside of this convex hull of rho, and it would have an eigenfunction at rho, corresponding just to the zero eigenfunction. So the imaginary axis you should think of as like the critical line, and rho you should think of as zero, but zero in different directions. Okay, cool. If we have some different functional, lambda, from A to R, then we can quantify how close the real part of that lambda gets to the real part of rho. So we introduce this notion of this polyhedral norm, and it tells you the ratio between this blue polyhedron and this orange polyhedron, or like the radius of that polyhedron. Okay? Okay. So now we have this polyhedral norm, and this is how we will measure distances in the sort of spectral world. Okay. Finally, if I want to quantify exponential decay of matrix coefficients. So before we introduced the matrix coefficients, but I didn't tell you that or I didn't quantify how they can decay. So let's do that now. We take some matrix coefficients V1 and V2. This should decay like or this should have the L2 norms of F1 and F2. And then we should get this decay, which is proportional to rho. And theta will be the infimum such that this bound is satisfied. Okay, cool. In which case, here is our theorem. So G is now, again, a real semi-simple connected non-compact Lie group, finite center. Gamma is just going to be some discrete torsion-free subgroup. So on the left, I have a bound on the real part of the spectrum. It's in terms of our weird polyhedral norm, but we can just ignore that. It's just a bound on the spectrum, on the base, on the bottom of the spectrum. In the middle, we have the behavior of the growth indicator function. Again, using this polyhedral norm. And on the right, we have the decay of matrix coefficients. So this is exactly the trichotomy which we had in rank 1, now lifted to higher rank in full generality. Okay. Moving forward. So in particular, we can characterize temperateness, and it's exactly the same thing. If the spectrum is fully imaginary, then you get temperateness, which confirms a conjecture of Hio, which was nice. I should say something because this work didn't come out of nowhere. Um, so in rank 1, it's often easier to work with convex co-compact subgroups. Uh, what this means is that you can control where the dynamics happens. So basically, if you cut off all of the funnels, you end up with something convex and compact. Um, so in rank 1, it's often easier to work with convex co-compact subgroups. In higher rank, um, I think everything is convex co-compact, or it stops having any meaning. And so people instead have turned their attention to P and Nossoff subgroups. So this is the analog. This is where people would expect things to be easier in P and Nossoff subgroups. Um, if you don't know what they are, they're a sort of form of mixing statement, but for the eigenvalues. So it's sort of saying that the eigenvalues um, separate in a nice way. Um, in particular, if you have the minimum parabolic, so Nossoff subgroups are associated to some parabolic subgroup. In higher rank, there are much more parabolic subgroups, and the minimal one is just the upper right-hand triangle. Um, so in this context, for P and Nossoff subgroups, Edwards, Lee, and O were able to control the asymptotic behavior of matrix coefficients. Edwards and O proved the temperedness statement for P and Nossoff subgroups, and then Day, Kim, and O were able to get this relationship between the growth indicator function and the Hausdorff dimension of the limit set um, for the minimum parabolic, and now you can generalize that to more general parabolic subgroups. So um, the upshot is that we don't need to worry about Nossoff subgroups because all of this is true for more general Lie groups. Okay. Um, okay, I still have 15 minutes, so I can talk a little bit about the proofs. And um, the proofs are all using uh, Harris-Chandra theory. So let me just remind you a little bit of some of that. We can define this elementary spherical function, which, okay, here it is. It's given by some spectral parameter, and then you move that by your rho. Um, this is a sort of odd transformation where you take uh, K, act on G inverse, that's fine. And then you take the A component. So you're looking in the Iwasawa decomposition. So this is weirdly mixing Iwasawa and Cartan decompositions. Um, and for basically the way we've set it up, you can see that this will be an eigenfunction for all invariant differential operators. So our goal is to use this as kind of like a fundamental solution to a differential equation and then build solutions by convolving things with this fundamental solution. And then it's a particularly interesting case is what happens when lambda is just zero. And this is what's called the Harris-Chandra function. And so, for example, people have studied the Harris-Chandra function, and um, we have reasonable estimates uh, for the growth rate. And then how are we even going to get to the spectrum? So in rank one, for a lattice, one has the Selberg trace formula. So if you want to answer a geometric question, you put that into the left-hand side of the Selberg trace formula, and then it will spit out some spectral theory, and you can start to analyze the different components of the spectrum. Well, here we don't have, in infinite volume, there is no trace formula. It's impossible to write down a nice spectral decomposition. But what we do have is what's called the abstract Plancherel theory, which tells you that if you have the right regular representation, then you can separate this into the different components on the irreducible representation. Okay, so how do we get decay of matrix coefficients from the spectrum, for as an example? Well, we take F and decompose it into its irreducibles. We take G and decompose it into its irreducibles. We can apply the Plancherel, and that pushes us onto the spectral side. Then we can just apply the triangle inequality. Uh, Again, this is just I guess that's Cauchy-Schwarz. And then we have bounds on the elementary spherical function in terms of Harris-Chandra spherical function, which we have bounds for as well, uh, coming from here, this bottom line. Okay, and then we end up here. We have the two L2 norms of F and G, and we have this exponential decay given by the real part of lambda, which is exactly the thing that we can control using our spectral estimates. Um, okay. We also need this analog of the wavefront lemma. Um, which is looking at this sort of correlation between uh, phi 1 and phi 2. And the point is, if h is some really, really big parameter in A, so you move out by h, and then you apply g, which near the origin, near the supports of phi1 and phi2, g might not be a big perturbation, but then over out here, it is a big perturbation. And then once you apply H inverse, all of a sudden you're in a completely different position. And so to prove this, you just look at the supports of either of these sets and you ask uh, how much of them will possibly overlap. Okay. Um, so now we can show that growth indicator bounds imply decay of matrix coefficients. So that's this inequality. Um, so we take some just general compact C, we automorphize it, and then we unfold it. That gives us this here. And then you can write that as exactly this wavefront lemma uh, in that form. We can apply the wavefront lemma and we get the necessary decay. Okay, so um, let me just summarize uh, what we went over in the second half. So the spectrum, if we think about just SL3R, then the spectrum lives on two copies of C. Um, the spectrum will live in this real polygon, which is just the convex hull of rho. It's yeah. Um, for an infinite covolume subgroup, the spectrum will actually live in one of these orange polygons and will be separated from rho. So we'll have some gap here. This gap then controls the decay of matrix coefficients and controls the growth of points in different directions. Okay. And then you can start to do more things with this. So for example, for SL3R, just because of the way uh, some of these transformations are set up, we were actually able to conclude that there is a point on this boundary of this orange polygon. So there is a point which actually has real part given by phi by pizza. Um, so maybe I'll stop there and see if there are any questions. Oh, thank you.
Thank
Okay.
you.
Thought that would
Let's let I'll stop the recording before we start asking stupid questions.